hasn't turned it in, make sure you get it right because I'm not going to give you a chance to do corrections. So these are the things that you should have had. For the very first one, I'm pretty sure I had a slide in there showing you this or something. So this was the one where it's on the launcher, and I'm just going to make the rockets look simpler than this in the future. So you needed to show the forces that were acting on it. There's weight, and there's you could call it the normal force, but I'm just going to say the launcher. And those are equal. So the net force is 0, and the acceleration is 0. So this would be for the pre-launch, before it's launched. Those are all the things you had to have on that. Now when the water's coming out, here it is, the water's coming out the back. Some of you didn't do a great job explaining this, but that doesn't really matter for this. Is this accelerating up or down? It's accelerating upward, which means there has to be a net force that's upward, which means that the upward forces have to be stronger than the downward forces. How many forces are there acting on this rocket now? Can anybody say it? Tell me quickly. 3. One is weight. Weight's always going to be acting on the rocket. Another one is the thrust, which is really strong, because it has to be strong enough to overcome the weight and what else? The drag. Or you could call it air friction or air resistance. So these are the forces you should have had for the second picture. There's going to be air pushing it down. There's weight pushing it down or pulling it down. But the thrust is bigger than the two of those, which means the net force is upward. Now the next one, this is when it's coasting. Coasting means there's no thrust anymore. So it's going to be just like the last one, except the thrust is gone. So if I make it just like this, except the thrust is gone, then I'm going to have weight going like this and drag like that. And if I add those two things up, what kind of a net force am I going to get? I'm going to get a downward net force, and that means I'm going to have a downward acceleration. So this is when it's coasting upward. And as it's coasting upward, is it speeding up or slowing down? It's slowing down. So does it make sense that if it's going up and accelerating down at the same time that it's going to get slower? Should. It should make sense at this point in the year. Okay, now when it gets to the very top, I don't really care how you drew it, but I'm just going to draw mine sort of pointing sideways. So here it is. It's up there. How many forces are acting on it at the top? How fast is it moving at the top? 0. So how many forces? No. What's weight? So it's still got weight. It always has weight, but there's no drag. There's no thrust. So that's it. So if I add up all these forces, they should be the same as the weight. The weight is the net force. And that means the acceleration is also downward. So how can it be that something is up there not moving, but it's still accelerating? What does that mean it's doing? It's starting to go down. It was slowing down on the way up, and now it's speeding up downward. It's just momentarily at 0. Can anybody tell me what the acceleration is? How many meters per second squared? -10 or -9.8. Because this is free fall. Free fall is when there's only weight acting on it. So that's the apogee. And then as it starts to fall before it gets to terminal velocity, it's going to turn around like this, and it's going to go nose down. My rockets are getting uglier and uglier as I draw here. There. So it's going like this. And before reaching terminal velocity, it's still going to have weight, and it's going to have drag, but which one's stronger before terminal velocity? Weight is stronger. And because weight is stronger, let me just write drag. That means the net force is down. That means the acceleration is down. So this is going to keep speeding up. It's going to keep speeding up, speeding up, speeding up. And what happens to the drag as it goes faster and faster? Well, no, drag isn't weight. Drag is the force of air pushing on it. Yeah, it gets stronger. So this is going to get bigger, and eventually it's going to get as big as this, and then it's at terminal velocity. So this is going down before reaching terminal velocity. When it gets to terminal velocity, it's going to have the same weight, but now the drag is going to be equal to the weight, and that means it's got 0 acceleration, so it's not going to change speed anymore. So the net force is also 0. So this is what it would look like at terminal velocity. And did I say it had the parachute? It doesn't really matter. I don't care whether you show the parachute or not, but there. I've got a parachute on it. I think that was it. As with regard to how the parachute works to increase I think the last slide was something like explain how a parachute works to decrease terminal velocity. Well, what the parachute does, the main thing it does is it increases the area of this, it increases the size, which allows it to have a big drag even when it's going slowly. So if you said something like the parachute makes it really big so it has more air resistance, great. That's how it slows things down. And on the very first one, the slide where you had to explain and you were supposed to have a slow motion video, what makes the rocket go up? Well, the rocket pushes the water down, and the water pushes the rocket up. And those forces are equal. The force of the water getting pushed down is equal to the force of the rocket being pushed up. That's Newton's third law. So if you want to fix